I'm Mr. Taru. In this video, we are going to do one of my favorite subjects in trigonometry or pre-calculus, and that is verifying trig identities or doing trig proofs. Now, we have a long series of videos to come based on this topic. This is the very first one, where we build on new properties and theorems and become more and more complicated as we go. So this is just the beginning, and we're going to be using the three Pythagorean identities, the quotient identities, the reciprocal identities, and some facts about being even and odd to help us work out these proofs. Now, these proofs are not going to be the two-column proofs that we did in geometry, where you had your sequence of mathematical steps in this logical order, and then a series of postulates and theorems and definitions and properties where you had to write every single line why you were doing what you were doing. That's not what these proofs are going to look like. We still have a lot of memorization we're going to have to do. These proofs are not going to include just, you stating transitive property or stuff like that. They're going to look like algebra. And we're going to have what basically looks like an equation with trigonometric functions all over it, sine, cosine, tangent, secant, and whatnot. And we're going to try and make the two sides match. But while they look like an equation, they are going to be a proof. So we're going to be basically doing some algebraic manipulation to one side of the identity to make it look like the other side. And when you get the two sides to match, well, then you're done with your trig proof. Now, you are going to be doing some algebraic manipulations, but it is not an equation where, say, you could add something to both sides or maybe divide something to both sides to make the two sides match. It's not an equation. We're not solving an equation. We're verifying an identity. So all of your algebraic work really probably should be on one side. In my classes, sometimes I allow my students to work with both sides of the identity. The very, very most important thing is, though, that you do not transfer terms from one side of the identity to the other. Now, to do that, like I stated, we're going to be doing a lot of substitutions with these Pythagorean identities. Some of these I've proven in other videos. We've got quotient identities, and another thing we're going to do in this video is a little bit of a time warp. Because while I'm pretty good at doing trig proofs, I'm sometimes not so hot at copying my notes. So I have another video, basically just redoing the introduction, where I had some miscopying from the notes as I got them up on my chalkboard. So while I'm right 98% of the time, actually I do care about the other 2%, unlike what this shirt says. So let's get to the examples in our first video, and this is a sequence of 3 videos to hopefully help you learn how we're going to be verifying these trig identities. Now let's get back to my other chalkboard, and it's kind of decorated for the holidays as well. And if we need be, I might erase my bottom set of lights. Yes, it is the winter season, the holiday season, and I'm going to be wearing funny shirts for the next 7 days. Hope you appreciate them, and hopefully it's not too hot when you're watching these videos going, why is all those lights up? Okay, and the holly. Anyway, we've got the cosine squared theta times the tangent squared theta plus 1 equals 1. And in my class, I jump around a bunch when I do these because I have a lot of chalkboards. I'm not going to be able to just run over and point to an identity that we're using, so hopefully you have that sort of formula sheet, if you will, copied down from the first few seconds of the video. So we have to, and what this is saying, by the way, this is an identity. It does work, but our job is to verify that it works, to say that no matter what theta is, when you plug it in, both sides of this identity are going to be equal. I can't call it an equation because I'm not going to be moving things around. Like I'm not going to divide both sides by cosine squared. So, what kind of substitution are we going to be able to do to make the two sides of this identity equal? Now, when you go to solve identities, or prove them, verify them, you want to make sure all the angle measurements are the same, and all my examples today are. This is the very first video of probably going to be a long series of videos for doing proofs. And you want to make sure all these angle measures are the same. And the next thing you want to do is you want to look for the 3 Pythagorean identities, like any of the big, heavy-duty identities. And right now we only have 3, the 3 Pythagorean identities. Sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared. And see if any of those big identities help to simplify and make these two sides equal. And then if there's if none of those identities will help, which they will with this one, then move on to, okay, all the angle measurements are the same. None of the three Pythagorean identities, which is all we know right now to help us out, are going to be of any great help. And there's no algebraic steps to do. Now we do have parentheses here, so I might be tempted to just distribute the cosine through, and maybe we will. But you want to look to see if any of the three Pythagorean identities are going to help simplify it first. If they don't, see if there's any algebraic steps that you can follow that are being asked in the identity. And then if that's not the case, your last step that you want to do is make everything in terms of sine and cosine. Sine and cosine are the two basic trig functions. They make up the other four trig functions. So if there's nothing else left to do, make everything in terms of sine and cosine, and then again allow the algebra to sort of like lead your way and attempt to make the two sides match. And sometimes you'll try stuff and nothing happens. You might go just down a long path and end up, let's just erase that and start all over again. Well, tangent squared plus 1 is equal to secant squared. So we can use one of our Pythagorean identities to take this part of the expression out and replace it with secant squared theta. And then we got cosine squared theta equals 1. Okay, well, we're really close to a final answer. This is just beginning introductory type proof, so it's nice and short. Secant, the reciprocal functions that I just erased, or the reciprocal identities, secant is the reciprocal of cosine. Instead of being x over r, it's r over x if you're dealing with the unit circle. Well, here we can write this as the cosine squared theta times 1 over cosine squared theta equals 1. And of course, whenever you divide anything by itself, you get the answer of 1, and bam, you're done. Two sides match. That says that no matter what the theta measure is, whatever the angle measure is, cosine squared times tangent squared plus 1 will always equal 1. So we just did our first proof. Pretty cool. All right, so I'm getting excited because I love these problems. Let's take a look at cosine theta over secant theta plus sine theta over cosecant theta equals 1. Now, on the left side I've got two terms, on the right side I only have one. A lot of times when you have a different number of terms on each side of the identity, you're going to want to find common denominators and add those two terms together and see what happens. And indeed we can do this, but and that's another thing too. When, like if I'm just teaching Algebra 1 and I'm letting my students or teaching my students how to solve linear equations, I can give like 5 steps. And if those students follow those 5 steps in a particular order, they're pretty much always going to get the right answer. Maybe a really difficult question might take an extra step, but I could say here's 5 steps, do them in this order. 95% of the time you're going to get the right answer. That's not the case with proofs. You might be at home finding common denominators or wherever, and putting these two fractions together to make one term. And that could very well be a correct answer. Please don't think what I'm writing is the solution. Many of these proofs have 3, 4, 5, 6, even maybe more ways to prove or make the two sides match. I'm just giving you examples. That's why the back of your textbook says proofs will vary. Well, secant is 1 over cosine. So cosine theta over 1 over cosine theta plus sine, okay, we have sine over of theta over 1 over sine theta. You see what I'm doing? I'm taking out secant and replacing it with its reciprocal identity, and same thing with cosecant. Now, you can take these bottom fractions and flip them up. You can't really, there really truly is no division of fractions. You multiply by the reciprocal of the second fraction. Well, that's always going to be your denominator. So cosine of theta times, this bottom flips up, cosine of theta times cosine is going to be cosine squared, plus, again, this bottom is going to flip up. You're dividing by a fraction, so you multiply by the reciprocal. So sine times sine is sine squared. And if you don't know your Pythagorean identities yet, go look at those notes you just copied or the back of the book. What's the first Pythagorean identity? Sine squared plus cosine squared equals 1. Now, I did a different looking proof for this in another video, Introduction to Fundamental Theorems with Proofs. You can solve this or prove the Pythagorean identity is correct by using the x over r ratios, the y over r ratio off the unit circle, do a little bit of algebra and incorporate the Pythagorean theorem and prove that yes, this does equal 1. However, we're not going to be proving the basic fundamental theorems or the Pythagorean identities. That's been done in a previous video. We're, of course, going to be doing some, well, more in-depth proofs. Not proofs that are going to be using just the ratios of x, y, and r, though you could do that as well. Let's take a look at another one. We got cosecant squared of, let's just call it x, over cotangent of x equals cosecant of x, secant of x. Okay, well, let's see what happens. Not much. There's no addition to work on. There's no common denominators to worry about trying to make. There's no multiplication or parentheses with exponents. There's no algebraic steps that I can do right now. So, well, I don't know. And so when you get to a point where there just seems to be nothing that you can work on, that's when you make everything in terms of sine and cosine, because again, those are the building block trig functions. And you also, when you do proofs, you want to attempt to work or start with the more complicated side and simplify. Think of like a tree. If you're at the top of the tree where it's all complicated and there's branches all over the place, and you work your way down the tree, you're going to come down that one trunk. Okay, you're going to simplify down to that singular answer at the bottom. Whereas if you start at the bottom at something simple and you start adding things and making it more complicated, you could go in all kinds of different directions. You could be anywhere up inside the tree that you lead yourself. So you always want to try and simplify, and these kind of honestly look sort of equally difficult or complicated. So I'm just going to pick a side and write it in terms of sine and cosine. So, well, this does have a power of 2, so let's work with that. Cosecant squared over cotangent. Well, that's going to be, cosecant is 1 over sine, so it's going to be 1 over sine squared x over cosine of x over the sine of x. Well, again, you have a fraction, and a fraction bar means division, so you have a fraction divided by a fraction. And when you divide fractions, you multiply by the reciprocal of the second fraction. So if it was written side by side, the denominator would be the second fraction. So you always do, I make this little pigtail notation, not that it's a real math notation, to remind you that we're going to take the bottom fraction and flip it up and multiply by the reciprocal. So it's going to be 1 over cosine squared times sine of x over cosine of x. Okay, well now you can cancel common factors. You cannot cancel out terms though. Let's take a look at, we got sine of the first on top, we have sine of the second on the bottom. When you divide like bases, what do you do with those exponents? Or you might just be saying, come on man, go ahead and just cancel those out. The one side on top will cancel with one of the two signs on the bottom, giving us 1 over sine x cosine x. And 1 over sine is cosecant. And 1 over cosine is secant. So bam! Look at that. We only worked with the left-hand side, and we got it to perfectly match the right-hand side. And I hear my alarm going off, so that means I'm getting close to being out of time. Sign me up or look me over for, look me over. How about check out part 2, where we do some more examples. Bam! Mr. Tarut, go do your homework.